Okay, let's think this one through together. Imagine we've done a series of experiments under different conditions, and now we want to quantify, measure what the different conditions, how it influenced, say, a particular protein we're interested in, or a hormone we're interested in, or a cytokine that we're interested in. How would we go about doing it? A classic way to do such experiments is to first, whatever protein or cytokine or hormone or whatever biomolecule we're trying to measure quantities of between different conditions or under different circumstances, we can go ahead and first obtain a reference pure amount of that protein or cytokine or hormone or whatever biomolecule. And once we have that reference material, what we will call a standard, we can go ahead and make serial dilutions of that standard. So we have serial dilutions of that standard, and then what we can do is measure the absorbance of the different amounts, because we've diluted it out, of the pure standard or reference molecule that we are also trying to determine in a sample where we're not sure how much is in there, depending on the different circumstances they've been in or different conditions we've treated it under. We can go ahead and measure the absorbance reading. When we do the absorbance reading, we will know the amounts that we have because it was a pure reference compound, a reference standard, a reference protein, a reference hormone that we went ahead and serially diluted. We know how much dilution we did, and so we know what concentrations we've done, and then by obtaining the absorbance readings of that, we can go ahead and use that information to to work out what amounts are in our unknowns. How do we do that? Well, the classic thing that is done is to first plot it. So you plot the concentration of the reference substance, the reference compound, the reference protein, cytokine, hormone, whatever it is. You plot it along the concentrations along the x-axis. And then on your y-axis or your vertical axis, you place what absorbance readings you obtain at each given concentration. So at each given concentration, you're going to have an absorbance reading that correlates to that. So you plot it all out, and the best graph to use for such an experiment is a scatter plot. So you do a scatter plot, and at each point at each concentration you will have a particular absorbance reading. So with each particular absorbance reading correlating with its concentration, what you need to do in order to be able to, in what the term that is used is interpolate an amount or infer an amount in your unknown based on the standard curve, is to obtain an equation of the graph that you've made. So you plot it, you get an equation of the line, and in order to get an equation of the line, you have to draw a line of best fit. The line of best fit is this idea that you can reduce the error around each of the points that you're drawing a line through. So if you're doing like a simple protein determination concentration, when you do the plot, you can go ahead and use a linear fit, a linear regression. And so you get an R-squared value that tells you if the linear fit is suitable for the kind of data that you have. And then you can also, in Excel, insert an equation of a line. If you're dealing with biological data, it's often that, such as you would be measuring an analyzer, it's often the case that you don't have a linear response with each concentration at each concentration. And so what you use is a sigmoidal fit. And so in this video, we're really going to get into how you can go ahead and draw your standard curve, putting a line of best fit, get an equation of the line so that you can interpolate or infer from that plot what the concentrations are in your unknown sample. And so we're going to look at 3 different ways to do this. We're going to look at Excel because Excel is readily available. However, Excel doesn't allow you to do a particular curve fit called a 4-parameter logistic fit. And this particular fit is required for biological molecules, typically because of the type of response, which is said to be a sigmoidal fit that you need. And so we, in addition to Excel, we will look at a paid option, which is like Prism, GraphPad Prism. And GraphPad Prism, I'm not really going to give you the details, and it's just to flag that that's an option for you, because that will be a software that allows you to do a 4-parameter logistic fit for your ELISA data. But the best part of this is I'm going to show you an online tool that you can use. You don't even have to download it. You just simply enter your concentrations for your unknowns, your concentrations for your standard curve, and it's going to be able to allow you to determine what your concentrations of your unknowns are. So if you're interested in something like that, let's get into this video. The way that these assays work is to first make concentrations, various concentrations of the particular hormone you're trying to, particular protein, be it hormone or whatever, cytokine that you're trying to measure, make several concentrations of a known amount. And this is going to be used to create a curve that is going to be called a standard curve, because it's the standard that you're going to compare your unknowns to. So say you've got particular hormones in blood from an experimental group, and you're going to want to know what the concentrations are after treating it differently, after putting it under different experimental conditions. The way you do it, one way to approach it, is to make concentrations of the particular hormone or particular protein that you're trying to measure, make several dilutions of that, and then measure the absorbance of it. And you also measure the absorbance of the concentration of the unknowns, the amount in the samples that you don't know. And that way you're able to work out what the concentrations were in the unknown sample by comparing it to the concentrations in the known sample. Now you make serial dilutions of the stock or the standard that you want to compare it to, measure the absorbance readings for that, as well as the absorbance reading for the amount in your unknown. And then the next thing to do is to plot the concentrations in order to obtain an equation of a line of best fit for the known concentrations. Now, since Excel is readily available, we can do it. We can initially look at how you go about it in Excel. So here are my known concentrations. I've obtained absorbance readings for it. With these kind of assays, you often have something called a blank, which is your background reading. You're reading when you don't have any of the hormone that you're trying to measure in there, and it's just in the reagent that you've dissolved it in. So that background reading is subtracted from the readings that have the particular hormone or protein that you're trying to measure. If you have a plate reader that has dual wavelength or multi-wavelengths, then you're going to be able to read the blank or the background reading and just automatically subtract it from the readings of the standards. The standards from the readings of the standards and unknown. So there's usually an option in your plate reader setting where you can check for it to show you the blank corrected values, the blank corrected absorbance values. So let's first look at Excel, where we will plot the standard, the absorbance readings that we got from the plate reader. And in this case, we actually know what the concentration is. So on the x-axis, we can put our concentrations against the absorbance readings, and this is going to be a standard for us. So we plot what the concentration is and what the absorbance reading was for that particular concentrations, and then we go ahead and fit a line of best fit. I have a video on here on how to determine what the best line of best fit that you should choose is, but in this particular video, because it's an ELISA reading and absorbance reading of particular concentrations, the line of best fit we're going to pick. We could pick a linear regression, we can pick a linear line of best fit, or we can pick, if you're doing ELISA, then it's recommended that you use a 4-parameter logistic fit. Now, doing a 4-parameter logistic fit in Excel is not possible. So that's when you can go and use softwares like Prism. Now, Prism, you have to pay a license for, you have to pay for it. So it tends to not be readily available, but I'm just going to flag it that that's one software that you can use to do your analysis. So with Prism, you're going to put your concentrations, your known concentrations from your standards and the absorbance readings you obtained from them, and then you're going to be able to enter your unknown concentrations. And because it's a great software that's been optimized for these sort of calculations, you'll be able to by selecting particular icons, you'll be able to get the unknown concentrations in an instant. But if you don't have Prism, there is actually an online tool where you don't even have to download it, called Arrigo, where you can go ahead and put your concentrations in there, and it will also tell you what your unknown concentrations are without you having access to a 4-parameter logistic software with a 4-parameter logistic fit capability. So here in Excel, you can see that we have it. The first standard is the top standard, the most concentrated of whatever hormone we are measuring. And that's the absorbance readings that we obtained. Now, the absorbance readings have already had the blank subtracted from it. And so it says blank for 50. If it hadn't, then we would go ahead and do that manually. And I know the concentrations because I created the top standard. Or if you used an ELISA kit, the standard would have come in it. Or if you're doing a protein concentration determination, you will probably have bovine serum albumin that you dilute serially to get particular top concentration that you then dilute out. So these concentrations are known, and we know what that concentration equates to in terms of absorbance, and this is how we're going to be able to work out what the concentration is in the unknown. So standard 2, I obtained these particular absorbance readings for that concentration. Standard 3, I got this sort of reading for that particular concentration. And so we go ahead and, depending on the number of standards we created, we obtain the absorbance reading, and there's always the one standard that doesn't actually have any of the particular hormone or protein or cytokine or whatever we're measuring in it, and that's the blank essentially that is used to adjust for the background readings. So I go ahead and take the absorbance readings, and as you can see, I need the 2 readings because I did it in duplicate, and so I'm going to take the average of those 2 readings for each of the different standards that I've created or that came with the kit. And of course, the last reading, the last standard, we get a minus, and that essentially just means 0. It just means it was really, really low reading, and the concentration for that, we didn't actually put any of the hormone that we're trying to measure, so that's 0, and we go ahead and take the average of that. So in Excel, we can go ahead and plot that by going to Insert, and we are going to insert not a bar chart because it's not individual, they are related to each other. So we're going to do a scatter plot. So go to Insert in Excel and use a scatter plot to get your point, and you can see that it's got the axes wrong. So let's just see what it's doing, and then we can guide it. So what we can see that it's got the concentration values in blue as a separate value to the absorbance reading. So these 8,000, 2,667 values have been separated from the absorbance reading. So we actually want that to be a part of the scale, the axis, rather than a separate value. So we can go ahead and point Excel in the right direction and tell it that that's not the comparison we want. And so we can go into, if you double click it, it will give you additional icons that you can, or options where you can adjust what is happening here. So let's go ahead and do that. By double clicking, I now have the option of, you can't see it on my screen, but if you double click, you can see, I'm just going to see if I can switch to the view. And by double clicking, you now see I have an option. You can't actually see it on my screen, but you can see where what it's showing you as the plot. So if you see these ones, it's used the concentrations rather than using it on my x-axis. It's gone ahead and plotted it separate to my y, and so we're going to change it. So by double clicking it, you can't see it on my screen, but you'll be able to switch the axes that you want it to use. And just on the top, the options become available. I apologize that you can't see it. But I have a video on here explaining how you draw your charts. So you can have a look at that. Maybe I can actually insert what I'm seeing here. So you're going to switch rows. So you're going to go to select data. Here we go. So I by double clicking, I had options to select data. So if I go ahead and say select data, you can see that it's put the standard 1, standard 2, standard 3 that I had as the x-axis, so horizontal axis, and then it's gone ahead and just put the concentration absorbance as variables. So I want to go ahead and change that. So I'm going to go and fix that up by I was able to select the chart range, and as you can see now, it's got the points here. If I double click it, you'll be able to see that these are what it's using in the blue as the absorbance values, and it's gone ahead and treated this as an axis value, which I love. And because there's just only one, I can get rid of the series legend because we don't need that. We're not comparing multiples. So I go ahead and change the title, and I can say hormone concentration in serum, and it was in rat serum. So we get that. And in terms of making the plot less intense on the brain, like giving it multiple things to think of when we only wanted to just focus on the concentrations of the serum of the hormone that we've measured, we're just going to go ahead and get rid of the grid lines that are not necessary, just to clear things out a little bit. And we can also add the axis titles. So I'm actually going to go ahead and just make that 0, this concentration 0, because it is 0. And that fixes the axis somewhat. And we're just going to let the viewer know what the x-axis represents. So once again, you can just double click, and you get add chart element option. And I'm going to go ahead and say axis, and I'm going to do a primary axis, and I'm also going to do an axis on the vertical side. Axis, I've named it, that is the absorbance at 450 nanometers. And what you can do is just select the x-axis, and we're just going to go ahead and make the line thickness just a little bit stronger. So it's just easier to see what the axis is. So I do the same on the x-axis. I just change it so that the line thickness is also bolder. So I go to about 1.5, and there you have it. You can clearly see the frame for my plot, and you can see my points here. We can change the point. I might change the point series to make it a different color, just so you can, so if you come here, you'll be able to go to the line, to the marker, and go ahead and change that to maybe red to stand out. And so this is the fun part where, okay, we've got this plot, but to be able to use it to determine the unknown concentration, we need something called the equation of the line. We need to actually have a formula for deciding what, based on the unknown absorbance reads, what the concentration would be. And so to do that, you have to fit a line, what's called a line of best fit. And from that, you'll be able to show the equation of the line. Select your plot once again, and you will see in add chart element, you will see the option of a trend line. And so we want to go ahead and select a trend line for that. So you can go into more trend line. So when you select more trend line options, it's gone ahead and just put a basic line, but this is where you can go ahead and choose what kind of line you want. So it's got a linear line. If you wanted a logarithmic line, you could select. So here you can see it's got a linear, logarithmic, a polynomial, and these are all based on how your values fall the shape of it. And I have a video on here that describes somewhat, not in mathematical forms because I'm not a mathematical person, but just in general what you are trying to do. And so with the linear fit, if we go and say display equation of the line, well, we wouldn't want to display an equation of the line until we know that it's a good fit. So if we say display r squared value, you see that we got 0.9534. The closer that value is to 1, the better. So 0.95 is probably not a great fit, and you can just eyeball it. You'll see that it's sort of going through these points, but it's ignoring these points down here and these points up here. So it's not the best line of fit, the best fit line for us. So if we display an equation for that line, we're not going to be very accurate in trying to determine our unknown concentration based on that equation. So we're going to get rid of that. We don't want that particular line of fit. So another option Excel gives you is to do a logarithmic fit. And for this particular value, Excel just tells you can't actually do that. So that's fine. We can go and pick a different line of best fit. So once again, if I come into trend line and more options, so I can do a polynomial fit. And as you can see, that's not, it's just as bad. If we display the R square value, it is slightly better. It's 0.9688. Gonna hope for a line. I'm gonna aim for a line of about 0.99 fit. So you can see it ignored these points. It ignores that point. It's a bit. It's close to that and that, so it's not too bad and it fits that perfectly. But there are no points in between. So we're not gonna bother. That's the equation that we would use, but we're not gonna bother to use that equation because we don't want. That's not a great line of best fit. So go ahead and remove that. I think if we increased the order to like a third order fit, then you can see it's improved the line of best fit, the regression, the line of best fit. And look, you can see it's going through this point and that point. So that's somewhat of an improvement. These are not too far from the line of best fit. So it could be acceptable. And so we would then display the equation, but we can get better than this because it's not going through most of the points. It's really only going through 2 out of the 8, even though these are not too far away. So what we can do is try a software that allows us to do a 4-parameter logistic fit. So Excel doesn't allow you to do that. It's not the best, but if you were going to use Excel, then this would be a better fit. So you could do the 0.9728 regression. You can insert your absorbances into this equation. Wherever there's the X, that's where your absorbance value would be inserted. But we can go to a software, free software. So you could go to Prism, and Prism would allow you to place your absorbance values against your concentrations, and then you could also put into Prism your unknown concentrations, and it will be able to give you readings based on that, and you'll be able to use based on a 4-parameter logistic fit. Prism, you have to pay for it, and so it's not easily accessible to everyone. So I'm going to show you one software you can use, an online tool that will allow us to do that without having to have a paid solution. So in Arrigo, it likes that the standard values are the raw values, so not the average, and it needs it to be side by side. So what I did was just to copy it, and then I used the paste transpose to have it side by side. So for standard 2, for instance, I just go ahead and copy that. And then if I come here to paste, I right click, and this is the transpose option. So it places it side by side rather than on top of each other as it appears here. And that's the right format for placing it into the data gain ELISA software that we're going to use. So in the gain data, Arrigo's ELISA calculator, you're going to go ahead and place the raw optical densities that we've obtained for the standards here, and then it will show us where it's fitting inside the well, and we can then go ahead and get our unknown values. So as you can see, it's placed it correctly. We've got our standards right here. We will get to assign which ones are standards over here. So let's go ahead and grab the unknown up to optical density readings, which will fill the rest of the wells. And then we can go ahead here and do the well assignment, so it knows which ones are standards and which ones are unknowns, and then it will be able to calculate the unknown concentrations for us. And so you go ahead, and once you've entered your experiment name, you select the regression model you want to use. So whether you want to use a 4-parameter logistics, 5-parameter logistics, or a linear regression model. For an ELISA data, you definitely use a 4-parameter logistics. If it was just a protein determination, you would select a linear concentration because you've got set responses that you are going to obtain. For normalization, you can either say you don't want it normalized at all, or you want to set the maximum response as 100%, or maybe you want to set the maximum response as 100% and then the minimum as 0%, and it will try and fit all the values within that, so everything is normalized against your maximum concentration response and your minimum concentration response. So that's the idea of normalization. And if you have additional things you want to apply, such as if you had brought in the raw optical densities without the blank corrections, then you would have gone ahead and set it here. But if you've already got the blank selected, subtracted values, so you could have subtracted the minimum from all other optical densities, then you select that as well. In my case, I brought in the blank corrected value, so there was no need to change anything. And then in terms of your plot settings, the scale that you want to use, you can use normal scale, or you can perhaps you want to use a semi-log, or you want to use a log scale. Then you go ahead and hit analyze. And in analyze, what you see is that it's going, because it's a 4-parameter logistics, it's going to apply 4 parameters in determining the equation of the line, where your A equates to the theoretical response you would have received at 0 concentration, so the concentration where you do not have any of the hormone present. Then B is the slope of the curve. C is called the inflection point, this may equate to your effective concentration 50 or your inhibitory concentration 50, and D is your theoretical response at infinite concentration. So in order for the software to give you a line of best fit, I had to go ahead and subtract the minimum in the other settings. You can't leave it blank. I needed to subtract the minimum from all other optical densities, and the minimum was my 0 reading. So I went ahead and ticked that. And here we go. Now I have a line of best fit for this. We're using the 4-parameter logistics, so you can see that was the equation, and it's gone ahead and computed the values. It's telling me my line of best fit is 1. It's perfect fit. As you can see, it's really going through all the points, all the values, and so based on that, it's been able to spit out an unknown value for me. So I'm able to obtain concentrations now based on it's based it on this standard curve, which was based, if you remember, on the concentrations that I have told it to calculate. And that's how easy it can be with these softwares. Rather than using something like Excel, you can go ahead and export it to Excel or export it to a PDF. But essentially, we've now got all our unknown concentrations. It even tells you the standard deviations for each of the reads. And so that's how you determine the unknown concentrations in your sample, whether it's a protein determination or whether it's a particular hormone or assay that you're doing, ELISA that you're doing, and you need to work out what the unknown concentrations are. So now you can go ahead and plot it in Excel to see the concentrations that you've obtained and beautify your graph, as I've shown in the other video, if you want to refer to it. So I'm going to leave it here. I'll catch you in the next video. God bless. Bye.